So, here's a chart I put together because, okay, well, kind of like show me the numbers here. So, there's several ways to monitor microseismic activity. You could do the stuff on the surface, you put all the sensors on the surface and try to monitor. You could put the things downhole with what are called analog sensors and digitize at the surface. You could put digital sensors downhole, and then you could do ours with fiber optics. I think the industry's generally come to the conclusion that putting sensors on the surface, you can't really hear the microseismic events. I'll show you why in some other slides. So, pretty much this has been determined. There's a lot of hype initially that you could use surface sensors, and they're inexpensive, but you really couldn't detect enough. The next thing is you put the sensors down, they're analog, and you have all the expensive digital electronics at the surface. It's relatively inexpensive, but it turns out it wasn't sensitive enough either. You pick up a lot of 60 hertz noise, electronic noise, and all that. It's relatively noisy, so it didn't really work well for microseismic. The current state of the art is a downhole digital system, and that's what people are using right now. And the noise floor is decent, but in reality, the performance is really marginal for microseismic, and what they're finding is they have to drill way down. Like, let's say you're fracking 5,000 to 6,000 feet, you have to drill the wells down and get the sensors really close to the activity. And the problem is that not only is the system expensive, but to drill deep like that is expensive. So, we are coming up with a fiber optic system. The cost of ours is much, much less because it's a much simpler system. Bandwidth, noise flow is better, and so pretty much meets the cost and performance requirements, and we can put them in shallow wells that cost less. Next chart. So you may have seen, we had a press release out maybe a few days ago about this license agreement with Northrop Grumman. And a little background is I used to run the group at Northrop Grumman, actually when it was Lytton, and it was acquired by Northrop Grumman. And we came out with a system while I was there for our nuclear submarines, where we put sensors on the side of the submarine using fiber optics. And the problem is the previous technology was conventional, it wasn't very reliable, they'd go to sea and had a lot of failure problems. So we had convinced them that, if you switch over to fiber, you'd have the electronics inside the submarine, optical fiber in the sensors outside the submarine, and if there's any issues with the electronics, you could change them underway and fix them, but there should be no issue with the fiber sensors outside the hull because it's just optical fiber and no moving parts, nothing to fail. We convinced the Navy to switch this from conventional to fiber. Won a contract on the order of $450 million. And the beauty of that system is that, it's on the first 3 submarines, the first 3 years they went to sea, where they're having on the order of 10 or 15% failures every time the submarine went to sea. In 3 years, with the fiber optic sensors on the submarine, they didn't have a single failure. And I talk to the guys at Northrop Grumman now, pretty much the same thing. They don't think after 15 or 16 submarines out there for a decade they've had a failure of a fiber optic sensor. So the reliability of fiber optic sensors is proven. And so we say, our technology is based on that. I used to run that group, and now, most of the key people that with that group are with us at USSI, and we commercialize that. But a lot of our guys that work for us work there, and they said, what, right now we're using a certain optical interrogator technology, but remember when we were lit at Northrop Grumman, we developed this really neat technology. We spent $30 million in a decade developing it, and it allowed you to demodulate the fiber optic signals in a personal computer. And it was really kind of novel back when we were doing it maybe 8-9 years ago. But the problem was that computers, it was sort of marginal because computers weren't that fast. But now with computers having these dual cores are so much faster, we could take that technology and make a PC-based demodulation system. The performance is far and away better than anything out there, and it's less expensive. So we made the decision, say, let's go back to Northrop Grumman. We know which patents they are. The guys that work for us are actually the inventors on the patents, so they know what to do with it. And let's see if they'll license it to us. And we're able to do it. And so we licensed it, and we signed the deal on the order of like a month ago. And so this is very, very important. So, this will be an industry first, a PC-based optical interrogator. Next slide. The other part is once you have this equipment, it's out in the field, they have to install it. And if it's really expensive to install, that's another factor in why people don't monitor more of the frac jobs. So there's a guy at Department of Energy, of course, they're trying to increase the monitoring, and they did several studies saying, like, wouldn't it be great if we could pick out an optimum depth that, we could drill a shallow well and get it, the sensors in a shallow well and monitor it rather than digging, drilling down to 5,000 to 6,000 feet. And they came out with a study and they published it that, what, really, if you can get the sensors down below 300 feet and they're low noise and sensitive, that's as far as you have to go. And so we like that. And this all comes from Ernie Major. He's the deputy director and geophysicist at Lawrence Berkeley Lab. And, he's published this, and the industry is really looking at it. We'll show you a little bit more about that later. But some of his test results, on next slide. Yeah. So, he said, I have to go out and confirm this. So he put some sensors in a well and measured, as you go down in depth, what's the noise? And he's saying that you get on the order of 50 to 60 dB lower, below the surface noise, getting down about 300 feet. But if you go deeper, you don't get that much more improvement. The beauty of it is that if you only have to drill a 500-foot well, they use different equipment for it. You could drill and case the whole thing for on the order of $10 to $12 a foot. And so you have like a 500-foot well, it's like $5,000 or $6,000, for frac jobs and stuff. This isn't a noise. Whereas if you want to go down and put a 5,000-foot well in, that could be hundreds of thousands of dollars. So, this is key to us because we make the low-cost sensors. They're very sensitive. We could put them in the shallow wells and make the whole process less costly. And then there's a couple other charts that he went out. He said, just want to say you got consistent results, measured different times, and all that. And each time he's able to show you get down, 300-400 feet, the noise floor is 40, 50, 60 dB. We're talking 1,000 times. 60 dB is on the order of 1,000 times quieter. So it really makes a difference. That tells you why when people try to measure stuff from the surface, they can't detect it because it's 1,000 times noisier at the surface. And so how are you going to detect these very quiet signals? Okay, next chart. Another things we're doing is there's one of the major oil companies, and we have agreements, so I can't kind of say their name, but we talk about what we're doing with them. They want to prove this out because they said, what, we want to monitor all the frac jobs, but it costs too much. And so they've asked us to put together a system, and we're working with them on this, is it said, we want to drill a well that's about 1,000 feet. And this kind of gives you an idea where their head's at. And so we're going to put like 6 sensors down around 1,000, and another 6 down around 750, another around 500, and we're going to monitor a frac job. And we're going to see, is there any advantage to being 1,000, 750, or 500? And their data showing that they could do this with 500, but they want to see it. And then based on this, they're going to use that to pick out what their optimum depth is for their frac job. So we're working with them, putting together a system for them to go out and do this. you know, another thing we did is, you know, so we go out and we test with people in the field, and we show how our data looks compared to, you know, their field testing, you know, in the field. But we go, why don't we do a controlled test in a laboratory that, you know, we control, you know, how much noise gets in, we control the bandwidth and sweep rate and all that, and we do a control test side by side with the best state-of-the-art conventional geophone out there. So, you know, we have something we can show people. So what we did was we took our fiber optic accelerometer, we took the Geospace Omni 2400, which everybody believes is the state-of-the-art, most widely used for microseismic monitoring, and then we have a reference Excel, and we recorded it on the Geospace equipment. Everything was recorded using the same parameters, and we have this test set up. And so this, you know, this is a shaker that's going to shake this, you know, assembly. Here, our sensors here, we have an X, Y, and a Z. We have the reference Excel stuck there, and this is the OYO geophone. And then we digitized it, and we looked at the data. And next chart. I don't want to, you know, there's a lot of junk up here, so I don't want to go into a lot of detail here. But, you know, the bottom line is, here's our sensors, and we swept from about 4 hertz to 400 hertz. So anything above 400, just don't pay attention to, because we only swept the frequency to 400. But we wanted to show that, you know, across that whole 400 hertz frequency band, ours was perfectly flat. This is very important. And then you look at the OYO, you know, it drops off with frequency. But then once you get up about 350 hertz, the geophone itself has all these spurious resonances. And basically, anything above that, those spurious resonances, you can't really use that data. So their bandwidth is limited to about 350 hertz, where we can go up to, you know, that sensor, you know, that we were testing there was good to about 600 hertz. We have others that are up to 1600 hertz. But there's no way a conventional geophone will get anywhere near that. So this is amplitude response. And on the next chart, I'll show you, there's a lot of details, it's called phase response. But what phase response is that you have a sensor, and if you have a pressure wave coming in, typically a pressure wave is like sinusoidal. So when it comes in, you want, if you have both sensors at the same location, the phase of that response, a sinusoidal signal coming in, should be identical. You want it perfectly matched. If it isn't, you know, there's a problem. So, you know, you take a look at ours, you know, the response is linear broadband, and the phase response is essentially matched perfectly. Whereas the geophone, it is flat, and because of the fact that geophone actually measures velocity and we measure acceleration, you know, it's offset by 90 degrees. I mean, you may remember from your calculus days, you know, that taking derivative velocity, you get acceleration, all that. Don't have to care about that. The point being is that, you know, it's flat up to about 350 hertz.